All right. Chapter 2 review video for MAP4C. Failed to mention a couple of things at the beginning of the Chapter 1 video. Um, One is that this isn't 3 minutes. It'll take a little while to get through these videos, but this would have been, had we had time in class, it would have been taken place of the 3-minute review. Also, there are copies where you clicked on this of the PDF of this. So instead of, if you wanted copies of this to study from, you don't have to madly copy all this stuff out. Print out the PDF and follow along. And that's completely up to you whether you do that or not. Here's chapter 2 was a lot of review. I think everything was review, but essentially we did all the hard problems. So you see all the topics there. Area of composite shapes. Composite shapes were, ones where more than one shape was jammed together. Volume and surface area of composite objects, same thing. So it's not just a box, it's a box with a triangle on top or something like that. One of the pains in our butt for this chapter was this idea of optimizing. And remember, the idea is you should have a good picture about what the best shape is. If it's area and perimeter, the best shape is a square if it has to be a rectangle. If not, the better shape is the more sides, closest to a circle if you have any choice. Optimizing volume and surface area, the idea is the closest to a cube you can get. For instance, in a cylinder, if we had nice cylinder there, but if the height and the diameter were the same, it's kind of like the QB cylinder. The QB cylinder is the best cylinder. And these facts you could write on your formula sheet. You can't write any examples, but you could write those facts. Best shape is a square. Best cylinder has the diameter and the height equal. Those sorts of things. And design problems were, again, those were the hard problems. That would make a good thinking question on the exam, these design problems, because you do have to think hard about them. This is a typical, example one's a typical optimization problem. 80 unbreakable patio stones and wants to arrange them into a rectangular patio. He will put a string of lights around the patio at $58 per meter. And we have to kind of decide what the shape is and whether this is area or perimeter or whatever. How should Ferd arrange the stones? Well, we know the best shape is a square, right? Best rectangle is a square. So we would like, right, where we're given the area is 80. We'd like to make it a square, right? The closest to the square, because that gives us the minimum perimeter. So we know that x squared is 80, and x is the square root of 80, but this isn't a whole number. If it was just fence, then we would make it the square root of 80, but these are patio stones, right? So we're not going to be able to break them. This is the idea of unbreakable patio stones. The closest we can get, and we'll have to find ways to arrange them that's closest to a square. So is going to be 8 stones by 10 stones. That's pretty close to a square. If we had one extra stone, we could make it 9 by 9. It would be perfect. So what we're going to do is we're going to make this Ferd's patio 8 stones by 10 stones. But now notice, we got to be careful here that this is in inches. Right? This is in inches. So how many inches is that? Well, each patio stone is 18 inches. So this is 10 by 18 inches, which is 180 inches. And this is 8 by 18, which is how many inches? I got it right here. I got it 144 inches. So what was the first question we were solving? How should Ferd arrange the stones? Well, this is the stones, 8 by 10 stones. So this is kind of the answer to A, and now I'm kind of in B already here, where what's the minimum cost? Well, what's the minimum cost? he wants to put a string of lights around the patio at $58 a meter. So we want the minimum perimeter. Now, of course, you see this is in inches, and the string of lights is in meters, so we're going to have to adjust this as well. So how do we do that? Well, we could change this to inches, or I'm going to find the perimeter in inches, because it's just 180 plus 144 plus 180 plus 144. The perimeter in inches, that's kind of a mess, 648 inches. And then I can use one of my conversion factors, which we did quite a bit. And the way this will work on the exam, by the way, is we'll have some facts on the exam. You don't have to write any of those, 1 centimeter is so many inches, 1 inch is 2.54 centimeters. These facts will be on the exam. And there'll be a couple, and you'll have to choose the right one to apply, but that's the idea. Isn't Mr. Restall so kind to you? You should be so thankful. Anyway, 1,645. We'll multiply, right? Each inch is worth 2.54 centimeters. So that's 1,645.9 centimeters. Changing to meters. Some of these, of course, you have to know from being alive in Canada. 6 meters, and then the cost. Each meter costs $58, so we multiply. Great question. This would be a good thinking question because it involves more than one step. That's an expensive string of lights. 68 cents. And a sentence. Okay, you got to write a sentence too. There's my sentence. You can do maybe better than that. All right, next one. Volume and surface area of the tier. Well, this is the idea of a composite shape. We don't have a formula for volume of tier shapes. What we're going to do is we're going to break it into a cone and a sphere. Volume of the cone. And this should all be on your formula sheet. Pi r squared h divided by 3. And the radius was... See, the diameter is 2, so the radius is 1. And the height is, of course, unknown, right? This is the slant height, and this is the actual height. How do I find it? Well, you know this is going to happen, right? Pythagorean theorem, that's 1, that's h, and that's 2. So in the Pythagorean theorem, I've got c squared, again, formula that you can put on your formula sheet if you like. The hypotenuse is 2 squared equals h squared plus 1 squared for, subtract 1 from both sides. H is the square root of 3, which is about 1.7, I think. Yeah. Millimeters. And then I can jam this into my calculator. That's a 3. Pi times 1 squared, all in one step in your calculator. 3.88 millimeters cubed. And then the volume of the half sphere. I'm just going to divide it by 2 at the end, I think, because we've got a half sphere. There's the formula for volume of a sphere, again, straight from your formula sheet, right? I'm dividing by 2 because it's only half sphere. The radius is 1 again. Jam that all in there, and you get 1.6. Oh, shoot, I mixed these two up from my notes. Sorry, folks. This one was 3.88 millimeters cubed. This one, sorry, go back and fix that, is 1.78. I was just looking off my notes wrong. And then the total volume is, how much? Here we go. I did it again. The total is actually 3.88. I blew it twice. This number off my notes is 2.1. I guess I'll know if you look at the notes who's just copying and who's following along. So this one's 2.1. The half sphere is 2.1. All right, so the total is almost 4 millimeters cubed. For surface area, I don't have enough room. I'm going to make a new page here. Surface area is actually a little bit easier because it's a half sphere. Plus a cone part, right? Now, if you look straight off your formula, you're going to have the formula for a cone is got this circle on it too, but we don't need to find the area of the circle, right? So it's just the curved part. And you kind of have to know your formulas so you know what the curved part is. So the cone curved part, not the circle. So I'm going to do those separately. Surface area of the sphere is, so this is for the sphere, it's 4 pi r squared, and then divide by 2 because it's only a half sphere, and see if I can get my numbers lined up on this one. And this is millimeters squared, and the cone curve part is going to be just the pi rs, right? No circle. The first part, pi r squared of that formula, we don't need it. Radius was 1, and the slant height was given this time as 2, and that is 6.28 as well. Coincidence there. And then the total surface area is these two added up is 12.56. The last example is one of these application ones. How many of these fit in the other one? This is an old country song, Tears in My Beer. There's a tear in my beer. If you just Google it, it's an old country song, and there's the YouTube. I know you can't click on it, but if you just YouTube it if you want to hear the song. It's a little bit funny. The question is how many tears would fit in this beer if it was half full? Well, I've been told that beers have 341 milliliters in them, which is actually 341 centimeters cubed. That's one that you should know. But notice that our volume and notice we have to decide, is this volume or surface area? How many will fit in, that's volume, right? So we're going to use that value there. This one, the 3.88. So how many of these 3.88s fit into this? Well, this is in millimeters, right? So we kind of have to figure out how many millimeters this is. Well, this is one of those tiny little cubes, a centimeter cubed. That's not bad, eh? Well, if that's 1 centimeter, there, and here, how many, oops, there, and there. How many millimeters is that? Well, 1 centimeter is 10 millimeters, right? So this is 10 by 10 by 10 millimeters. This volume, 1 centimeter cubed, is 1,000 millimeters cubed. So this beer is, one beer is a lot. 341,000 millimeters cubed, but we only have a half beer, which is half of that. That number times a half is 170, 500, and we got to figure out how many tiers go in there. 0, 5, 0, 0. how many the small go into the big. Is a lot. 43,000 tears in your beer. Okay, that's it for chapter 2. The next video is on stats. I think it'll be a little bit faster than this. Great thinking problems for an exam here, folks.